So let's start. Hello again, and welcome to this day 3 of our training, because the Monday was the first day and yesterday was the second. This is the day 3. And today we are concentrating in collaborative robots and also a bit in quality assurance oriented robots, although machine vision systems in robot solutions is our main subject just in the last webinar on Friday. Some of you have already brought nice examples to the chat according to our first assignment. I'm sorry, I didn't notice that the sharing of a file in chat was that complicated. So that's why I changed how the next assignment will be done. If you haven't yet bring your own example to the chat, please remember to do it before Friday. And of course, again today, I want to emphasize again that you can, anywhere in the lecture, pause and ask if something is bothering you. Just unmute your mic and ask. You can also post questions in chat. Again, Janika is here to follow the chat and point out if there is a question. Okay. Let's start with the definition of robots, because last time we ended to consider the definitions of different types of robots. Upon request, I have tried to bring important matters related to the latest robotic solutions to this training. And so I didn't start with the definition of the robots on Monday. But since it sparked a conversation last time, let's start with this time. Personally, I rely on the definitions coming from the standards and also from the International Federation of Robotics. And I brought them here in a really short form. According to ISO 8373 standard, robots require a degree of autonomy, which is the ability to perform intended tasks based on current state and sensing without human intervention. For service robots, this means that a service robot is a programmable device with at least 2 degrees of freedom. It moves in its environment and performs the tasks assigned to it with either partial autonomy or full autonomy. A service robot performs tasks that benefit people and other devices in a non-industrial environment. There are service robots for personal use and service robots for professional use, and they are distinguished from a commercial point of view. So a service robot for personal use means, for example, the robot vacuum, so it's only for your use. But then when it's for professional use, it could be, for example, a surgery robot. Then there is a professional doctor who is using the surgery robot. Then the term industrial robot is based on the definition of the International Organization of Standardization. It says that an industrial robot is an automatically controlled, reprogrammable, multi-purpose manipulator programmable in 3 or more axes. So it means there's really 3 axes or 3 freedoms with the robot. That robot can be either fixed in place or mobile for use in industrial automation applications. Reprogrammable means that the robot is designed so that the programmed motions or auxiliary functions can be changed without physical alternation. Multipurpose, again, means that the robot is capable of being adapted to a different application with physical alternation, where the physical alternation then means that the alternation of the mechanical system. And axis is this in this context means that the direction used to specify the robot motion in a linear or rotary mode. The robot can thus travel forward and backward, right and left and up and down. When it can do all these, then it has at least 3 axes. Today we are talking about collaborative robots, which are clearly counted as industrial robots, even though they have different characteristics than traditional industrial robots. Another type of robot we have already referred to is mobile robots. Last time, I think it was Dominic who asked about which group of mobile robots belong to. And currently, mobile robots are counted, at least in general, as service robots. They generally have 2 degrees of freedom, so they cannot be counted as industrial robots. They also serve humans or other devices like other robots, so they can therefore be counted as service robots. On the other hand, mobile robots are currently the most widely used in industry. So from that point of view, they could be also counted as industrial robots. Personally, I think that the number of degrees of freedom, so the number of access, is what matters. It can also exclude from robots all other hardware and especially software solutions that is often referred as robot. You know, some kind of a machine could be called as a robot. But if that machine doesn't have at least 2 axes, when it can go back and forth and right and left, then it's not a robot. It's just a machine. Okay, this was just because we were talking about this last time. And then I think that we can go to the collaborative robots. In the first webinar, I already referred many times to collaborative robots. They are certainly one of the most talked about reforms in the field of industrial robots and intelligent manufacturing today. And one hint, if you want to follow interesting articles related to collaborative robots, I shared the link to Robotics blog. Robotics is a manufacturer of especially various peripherals of collaborative robots, such as tools and sensors, which we are talking about on Friday. And I think that they have an interesting blog on the subject, which is worth following if you are interested in this topic. Okay. Then going to the collaborative robots, and I think that we could start with a little philosophy here. Originally, collaborative robots were based on the idea that why a robot and a human could not work closely together if it's safe for a human. One goal was to make the hit on the collaborative robot feel the same as the hit on the stationary robot. So it doesn't matter whether the robot is moving or it's there still. The hit, if you walk and hit it, it will feel the same. In principle, therefore, a person's own action would determine how much this hurts. Okay, the next question then was whether a touch that does not feel anything once or twice will at some point be painful if the touch is repeated frequently. And what all affects it, like human factors, ergonomics, etc. Okay, what has human-robot collaboration been before? Maybe you know the abbreviation HRC. In this context, it means human-robot collaboration. So what has it been before? What is it now? And what we expect it to be in the future? Before, there was no collaboration. The big and powerful traditional industrial robots in no way noticed the presence of a human being. They didn't stop if a human came to the work area and could thereby cause even really dangerous situations. As you can see in this series of pictures here. This is what it has been. Okay, today, I think that we are already in the situation where, thanks to collaborative robots, humans and robots can really work side by side. However, it still requires a wide range of monitoring. Let's look at this picture. First, as you can see, here's the robot, and this is the monitored area here. And the robot's end effector follows the operator's hand here. And the operator's hand is tracked by the system. And the the collaboration modes can be specified by the operator's voice commands. This is quite new thing here. Okay, the parts of the scene considered as the background, and then the parts to be assembled are here. So these two really can work together because the robot always knows how to act if the human comes to the same working area. In the future, a lot of development is hoped for human-robot collaboration again. Could there be a sensible, unpredictable conversation with the robot? Or could the robot keep us company and entertain us while it is constantly learning what we like and what we don't like? This picture here tries to show that. Okay, why do we want humans and robots to work together, side by side? This figure here, coming from ABB Robotics, shows alternative production methods and when the use of either is somehow justified. Let's first look at the figure using horizontal variables. On the left, the lot sizes of the production are low, and the number of different variants is high, and vice versa. Low number of variants here and high lot sizes here. Then look at the vertical variables. At the bottom of the figure, productivity is low and flexibility is high. And again, vice versa, high productivity up here and low flexibility up here. When manufacturing low lot sizes, like here, but a wide variety of variants, the work is still often done manually. Then it is known that productivity will be low, but at the same time, it is possible to do production very flexibly. Then we are here in the manual assembly part of this figure. If, on the other hand, high lot sizes of goods are made and there is a little variation, it is worthwhile to handle the production completely automatically. Then, of course, productivity is high, but on the other hand, there is really no flexibility. And then we are here on the automatic assembly. These are the options we are already familiar with to organize production. But here, in the middle, we have collaboration. Collaboration where robots and humans work together. Then we get the good of everything, but on the other hand, we may not get the best of everything. However, the collaboration will make it possible to improve the flexibility and versatility of automatic manufacturing. Let's take a closer look at these 3 steps in which robot safety has been developed. First, the robots were separated from humans by different safety systems. No collaboration between humans and robots was possible. Since then, a variety of applications have been developed that have improved safety and at the same time made it possible for a human to pop over the working area of a robot, for example. There may even be a safety mat, like in this little image here. There may even be a safety mat around the robot with red, yellow, and green areas marked on it. As long as the human remains in the green area, in other words, furthest from the robot can operate at full speed and power. If a human then steps into the yellow or orange area or closer to the robot slows down its activities to the level of collaborative activity. If the human then still has to pop in the red area, the robot will stop completely when the safety mat announces that the human has entered its working space. And the robot restarts again when the human leaves the red area, comes to the orange area. The robot is working with less power and less speed. But then when I come back here to the green area, then the robot is working correctly. But when we are talking about collaborative robots, we don't just mean an application surrounded by a collaborative safety solution, but we are really talking about safe and harmless robots that allow the robot to actually work in the same space as a human. So the robot is not stopped if I go there, but I can work together with the robot. When collaborative safety solutions are used, they are just safety applications. But collaborative robots themselves are safe and collaborative machines or robots. Let's then think about the real collaboration between a human and a robot. In such collaboration, it is always the human who decides what to do and how to do it, within the performance of the robot, of course. Instead of replacing a human with a robot, the intention is to bring a robot to help the human to do the work. As in this picture here, where this man is doing complex assembly steps and the robot is helping by bringing just the right parts at the just right time. Human is always quite adaptable, creative, deft, while robot is uniform, tireless, and strong. Thus, man and robot complement each other and thereby enable faster and more precise work. In this picture here, a human and a robot work together to move these boxes. The robot is the workhorse. In other words, it lifts the heavy boxes and constantly senses human control movements when the human task is to move the robot by hand to the right place. These are very good.
Excuse me, I have a question.
Yep.
Can the green robot move without the man placing his hands on it? Can he move by itself?
Yes, it can be programmed also to move itself. But in this application, it is made so that the robot all the time senses how the man is, handling it and goes to the.
Because it's a collaborative. Otherwise, it wouldn't be any collaborative. It would be dangerous.
Yes, yes.
Okay, thank you.
Yeah. So it can be programmed to move itself, and you can also use the control. A human can be there in a distance with the robot, and you can control it with the pendant. And then there's also this collaboration mode where the human takes the robot and moves it to the right position. Yeah. Okay. So what exactly is a collaborative robot? As we spoke, the term itself refers to robots that can share the same workstation with a human. In general, a collaborative robot is an application rather than a single or specific brand of robot. Actually, a collaborative robot alone does absolutely nothing, but it always needs at least a tool to do something with it. Then when considering whether a collaborative robot is safe or whether it is really collaborative, we must think about the whole application or solution, not just the robot. It is also especially important to consider a tool at the end of the robot's arm that interacts with its environment on an equal footing with the robot application. Look at this picture here. It doesn't matter if this robot is a collaborative robot or not. Its tool is a chainsaw, which is which is by no means a collaborative tool, next to which a person could work safely. So don't trust the robot to be a collaborative robot, but do a risk analysis from the perspective of the entire application. Collaboration or collaborative literally means activities where someone works together with someone else in order to make or create something. When talking about the use of collaborative robots, we often end up only considering the ways in which different robots are used in different locations. When it would be more important to think about how the robot works, in other words, what does it do and how? The lack of safety fences does not mean that the robot is a collaborative robot, of course. Actually, there are 4 different ways to work with a robot, but only one of them is the one that does not require any safety features. Let's see these. Let's take a look at the definition of the collaboration when talking about collaborative robots. First, monitoring forces and speed plays a key role in thinking about what is collaboration and what collaboration really means. When reading standards, 4 different ways of collaboration are found, all of which can be utilized in organizing collaboration between a human and a robot. First, it's called safety monitored stop. This means collaboration where the robot stops if a person enters the robot's workspace and resumes automatically when the person leaves the room, as I was telling about the safety mat. So it's an application. Then another one is hand guiding. This means a situation where the robot acts as a workhorse, like we saw in that picture. In other words, it uses force to carry some pieces, for example, and the human then controls the robot along its path. And the third option is speed and separation monitoring. This in turn means a situation where the robot avoids collisions with the help of various sensors and other safety devices. All these 3 are applications where we could use even the traditional industrial robots if we have all the safety equipment in our application. But the last option is so-called power and force limiting with inherently safe design or control. Yes, that's coming from the standard, that long part of the name. This means that the power and force of the robot is technically limited, so small that the robot does not hurt a person when it hits a human. This is the only option where no other safety solutions are needed, and the robot can really work with a human in the same space. And again, if you want to read more about the standards and about the risk assessment of collaborative robots, there is also one very good article about that in that robotic blog. So here's a link to that. Okay. Collaborative robots are thus designed to work together with a human in the same workspace. Such collaboration is made possible with technologies such as force feedback, low inertia servo motors, elastic actuators, and collision detection. It's a technology that limits their power and force capabilities to levels suitable for contacts. So you can contact with the robot, but it doesn't hurt you. Collaborative robots are generally more compact than traditional industrial robots. And when there is no need to build any safety fences around them, the space they take up is very small when the robot is not in operation. Features that increase the safety of the robots include, for example, lightweight frames with soft, rounded edges and minimized pinch points. You know, you can't see any hard corners here. For example, in this Yumi robot, sorry, the cursor didn't show to you. So you can't see any hard corners here on the Yumi robot. And all these axes, they are really, really soft. So whether you hit the robot or not, it doesn't hurt you anyway. Yes. So what are the main benefits of collaborative robots? First, they are flexible and very easy to use. They are also quite lightweight. Then I wrote here that they are inexpensive compared to traditional industrial robots. This may need some thought and explanation. When comparing the same basic features, such as reach and payload, some traditional industrial robots may be cheaper than similar collaborative robots. There are no major differences in the prices of high-quality robots in one direction or another. But traditional industrial robots always require a wide variety of safety solutions around them, which in turn collaborative robots often do not require nearly as much. In this case, the price of a traditional industrial robot cell will certainly rise higher overall when we count all those together, the robot and the safety equipment that we need. A collaborative robot is usually easy to set up and, on the other hand, move to another location. They also fit into small spaces because they don't need robust safety solutions around them. Well, collaborative robots are they are specifically designed to make human-robot collaboration safer. The really big thing in many companies is also that collaborative robots do not require any special programming skills. In many small and medium-sized enterprises, the company's own personnel have taken over the robots and built the necessary automated solutions with them. In summary, therefore, collaborative robots are tireless, additional hands that are easy to deploy. After this webinar today, I can share you one example from Sweden, where was this machinery company, and they started to use this kind of collaborative robots from Denmark, from Universal Robots. And their own personnel learned how to program these. It took about 2 weeks when they learned to program these robots. And they have told that first they bought 3 collaborative robots. And in less than 2 years, they had already bought 40 collaborative robots. And they had to also have more employees because their productivity had grown so much. But I can share you a link to that story It's very nice, and there's also a video in YouTube, but I can share it to you after this webinar. Okay, so what kind of work tasks should you plan for a collaborative robot? They are used a lot in packaging tasks. Then a person can be involved in packaging if it needs to be done more flexibly. For example, like in here. Collaborative robots are also good for palletizing boxes, like here, especially if space is tight, or the space also needs to be used for human work or movement. We have found a lot of such items in SMEs in the food industry, for example. Then they are good at machine service. This is an example from that Sweden machinery. They can, for example, lift blanks from the pallet and feed them to the CNC machine and then stack the finished products from the machine to another pallet again. Different kind of pick and place applications and different kind of installation work are also suitable tasks for collaborative robots. And in fact, in all of these tasks, the collaborative robot can do quality control at the same time. Connecting a machine vision system to a collaborative robot is usually quite simple. And many collaborative robots already have integrated machine vision. Now I have a question for you. What tasks would you give to collaborative robots? You can open your microphone and tell, or you can write your thoughts into the chat, and then I'll read them aloud here. Please make some suggestions. Where would you like to use a collaborative robot? Can you give an example? Now I just have to find the chat and see if you are there. Yeah, heavier object it could fit, which really saves the human. Yes, that's correct. Actually, I have a video today where I show you the largest or the strongest collaborative robot at the moment, and it comes from Fanuc, and they are those green robots that I already showed you, and the largest one can pick 35 kilograms. Yeah, glue stuff is very good because yeah, we can add machine vision and we can follow the line, for example. But also, if we know where the object is, we can glue stuff. And decorations on objects. Okay, yeah. Cleaning dangerous places and objects. Yes, very good example. Yeah, because we can put them to dangerous places and then any human doesn't need to go there or touch any dangerous object. In the small space, yes. We had this quite large project where we worked together with food industry SMEs. And in those places, they really have really small spaces where the robots could be working. And in those spaces, they can't use any traditional industrial robots. So these are a solution for SMEs. I'm sure of it. Okay, I think that if you didn't figure out any examples yet, I'm sure that they'll definitely come up later, and you can bring them up in the task before the last lecture if you want. But we have an assignment concerning this part. Okay. Then when planning the implementation of a collaborative robot, the whole can be planned based on the process or on the size of the robot, on the size of the parts, or on the risk assessment. Each case should be planned separately. So if you have planned one collaborative robot solution, it doesn't mean that you know how to work in the next. One has to think about what are the critical properties of a robot cell and then make a design based on them. So although we have a collaborative robot, although it's safe for us, we don't just trust to that. We have to check the whole big picture. How does the robot work? What kind of a tool does it have? And so on. So we always have to make the risk assessment. And again, I share one link to you. There is this is quite funny example of a collaborative robot where the collaborative robot itself is telling how, okay, of course it's not the collaborative robot because they don't speak, but they have done the video so that the collaborative robot is telling about its job. How does it work? How does it sense that there's somebody it should be avoiding collision and so on. But you can I can share all these links to you after this webinar via chat, but also you will get all the slides in PDF format, so you can also use the links from them. Okay, let's see one example of collaborative robots in use. This comes from FANUC. Let's look at one example of capabilities of collaborative robots in practical tasks. I have to say that I do not have any purpose in any way to promote the robots in these videos, but I have chosen videos completely due to their informative aspect. FANUC seems to have currently the biggest robots, as I told you, in this category of collaborative robots. And when I say the biggest, I mean robots with biggest payload and reach. So let's see how they can work and how large spaces they can use. I think that this is the biggest reach. And these are the maximum speeds, but we have to remember that when we are using these robots in collaborative mode, then the maximum speed is 250 millimeters per second. But then if there's no humans around it, then it can use those maximum speeds. But as you can see, he could just touch the robot to stop it and then start it again by pushing the button.
So it's 250 millimeters per second, the maximum speed for collaboratives. It's mandatory?
Yes, 250 millimeters per second. So when it is in the collaborative mode, then it can't have faster speed then. Yeah.
Why are these both collaborating and non-collaborative? Can they be both, or a robot is born collaborative and never changes a scope?
Very good question. Yes, they are both.
Oh,
Actually, most of these collaborative robots, they can be also used with faster speed, but then we have to have other safety equipment. We don't have to have any fences, but we have to have, for example, a machine vision system or a scanner which scans if humans are there. And then if the humans are coming closer, then they have to drop down the speed to the maximum speed of collaborative robots. So it's then 250 millimeters. But if we are, working hand in hand or arm in arm, like I said yesterday on Monday, then if a human is working there, then the maximum speed is always 250 millimeters per second. So we can use these collaborative robots, we can use them also in between of the real collaborative mode and the traditional industrial robots. There is this one part. We can use them without any fences, but we have to have some kind of safety equipment if we want to use more speed. And again, in many places, they are also using the higher speed. Here is how there are some buttons which can be used when controlling the robot really easily. So when you are working close to the robot, you don't have to be a programmer to use the robot. But the robot can be programmed so that it understands the basic controlling that you are using. For example, this robot here is doing a quality control. As you saw, there was a camera on it again here. Different kind of examples how to use these collaborative robots. Okay. Here it was. I didn't remember this. On Friday, when we are talking about machine vision in robot controlling, then we are also looking at these different methods how to control the robot with cameras. Okay. All right. One really interesting add-on or feature is remote recognition. It is based on capacitive sensing, and that's why it's called capacitive skin. There are two different versions of it. The first is the kind that is shown in this picture. So basically any robot, even a traditional industrial robot, generally, can wear such a cushion suit with integrated capacitive sensing that can identify or recognize a human even before it hits a human. From even 20 centimeters before the robot hits a human, it can recognize a human. In the second version, capacitive sensing is integrated into the robot. Let's look at an example of that. This company is making these robots with capacitive skin, and these are universal robots, and then they are making their own capacitive skin to the robot. So as you can see, it don't even touch human, and then it senses that the human is there. And then it also senses all the touches that the human is making, and it can control the robot really easily.
Can you go higher than 250 with this stuff on?
With this, actually, they don't recommend it to go higher. But I have read about it wasn't these vocal robots, but it was the earlier that I showed the cushion suite. It comes from Bosch Rexroth, the company Bosch Rexroth, and I have read about an experiment where they tried to use that with higher speeds, and up to 500 millimeters per second. It was quite safe. But when the speed went up from that, then it hit almost every time. But they don't recommend use speeds more than 250 millimeters if a human is there. And that's really easy, because normally when I'm moving this collaborative robot by hands, it's not that easy as it looks with this capacitive skin. And on Friday, when we are talking about more about the sensors, I will tell you about another like this, about the same. Okay, let's think a little more about human-robot collaboration opportunities. Collaboration, therefore, requires the actual collaborative robot, but also safe accessories and the process itself. This inherently enables safe collaboration. The goal is that human would no longer need any user interface to control the robot, but everything happens naturally so that the robot follows human gestures, expressions, and movements. When the robot forces can be controlled in real time, these robots can be used for ever newer and more complex collaborative tasks. Let's look at another example where human and collaborative robot work in close collaboration on BMW's assembly line. And after this, we will have a break, because now I noticed that it's almost 5 to 4 in Finland. But let's look at this. Now we have the explanations also, all in English and in German, if some of you is German speaking, so you can also read them. So the human is doing the complex tasks. She should be moving all around and, bringing new parts there. And now look, now it says the robot that now you can come here, and the robot, okay. Soon there will be a collision between this worker and the robot. Now this didn't went as it should be, and now she repairs it, and then the robot comes here, but the robot stops when it hits the worker there, and again here. While a traditional industrial robot, it just crushes the hand, and so we can't work with them. Okay. Okay, it's now 15:56 here in Finland, so it's 14:56 in Central Europe. I think that we could have the break now. We will have a 10 minutes break, and after that we will continue and look more examples, and examples also from our laboratory. But now let's have a break. 10 minutes. We will continue 6 after 4, or okay, 7 after 4, or 7 after 3. What's the correct time for you? Okay, we can continue. Let's continue with a little about those dangerous situations. For each collaborative robot application, we need to think that even if the robot is a collaborative robot, it is still part of a machine. In fact, the robot does not even need the CE safety mark, and no safety devices are needed because of the robot. So my point is that it is important to do a risk analysis for each application. Just look at that picture. We can clearly identify a universal robot, a collaborative robot from Universal Robots. But what does it do? It uses a table saw, and this person here holds a pipe to be cut with this table saw. After all, the robot as the saw operator removes this protection from the front of the saw blade, and the saw blade can very well cause injuries to people. Such is by no means a collaborative robot application, even if it uses a collaborative robot. If any part of the application can harm people, the application is not a collaborative application. So we have to make a difference between a collaborative robot and a collaborative application. And only if we have a collaborative application, then we can make humans and robots working together. Here's an example I took from SICK. You know SICK, the large multinational company. This example is about so-called mobile cobots. So these mobile cobots, Klaus and Clara, work at Continental's auto parts plant in Germany. The mobile robot, we can see a mobile robot here and here. If I remember correctly, this is Klaus and this is Clara, or Klaus. I'm not sure how it's pronounced. So both of them have a mobile robot and a collaborative robot connected together. The mobile robot transports the collaborative robot on its ride from one testing device to another as needed. When the mobile robot reaches the right point, the collaborating robot lifts the last tested part from the test device to the conveyor and transfers the new part to the test device again. Then Klaus or Clara can move on to the next test device again to do their job. Mobile cobots, so cobot, collaborative robot, and then it's mobile, so that they are now called mobile cobots, are absolutely sensible choices for a production where the robot doesn't have enough to do in one place, but could work 24/7 for different locations. However, one thing is important to keep in mind when talking about mobile cobots. The mobile robot and the collaborative robot on board must never move at the same time. That is, if the mobile robot is transporting the collaborative robot to the next workplace, the collaborative robot must be still in its transport position. When the collaborative robot then starts working, the mobile robot needs to stay still. By the way, there is more talk about mobile cobots in Talent Journey's service robots training, if you want to hear more about mobile robots. As we agreed before, mobile robots are counted in service robots. Okay. This example is from our lab here at Satakunta University of Applied Sciences. This is the first collaborative robot we've acquired 5 years ago. It is a Universal Robots model UR5. It is still our most used robot because its programming is really quick to learn and can be used even if there are a lot of guests or students in the lab. In this example, the robot is programmed to pour coffee and fry waffles. Unfortunately, the duff in the lab was not allowed, so the video shows the oiling and turning of the waffle iron, after which the finished waffle just appears for the robot to process. But let's see, I'm hoping that, but I can share a link to this also afterwards. I hope that you can see it. The video is made so that the robot is speed is 2.5 times as it really is, because these can't be done very quickly. Now it's oiling the waffle iron. This example is made to a local cafeteria entrepreneur, and it is made by our Robotics Academy students. And you can see the picture from above here. Now, and in this part, the robot should, take the duff to the waffle iron, but as we didn't have permission to do that in lab, now this video is made so, and that one is 3D printed just for this purpose, so that the robot can turn the waffle iron as it should be turned. Now the waffle is ready. And now, as you can see, the waffle appeared there, because now the robot is sticking this stick into the waffle so that it could be given to the customer. And next, some coffee. And again, because we only had this one tool that could be used in this example, they 3D modeled and 3D printed a new, what's that? A new way to handle the coffee pot. So this one is 3D printed. And then the robot is programmed so that now it turns the pot in the right direction, and then it takes the pot and it pours the coffee so that for each cup, it turns a little more of the bot. I brought this example to you because I wanted to show that these students, they started to do this example so that they didn't have any experience of programming this kind of a robot. And all this is done actually in 2 weeks. For each cup, it turns a bit more of the pot so that it can give 5 cups of coffee with the same amount of coffee in them. Now you can see that there's the same amount of coffee in them. Okay. This next example has also been done with collaborative robots found in our lab. This example demonstrates a situation where a user can place a desired order for robots, and together they perform a task. In this example, the user can order the desired block pattern. You know, these are examples coming from the lab environment. So and the robots together retrieve the blocks and form the desired pattern. The video will open in another window, so we'll make sure it is visible to you first, and then I'll start the video. Okay, we have a Yumi, IBB Yumi, and there is the block order that I have ordered, or the block pattern, sorry, that I have ordered. Then this Omron collaborative robot, it finds the desired block from the sloping plate and brings it to ABB Yumi in this point. And then Yumi checks with its camera that it's the correct color and places it. And again, this Omron TM12 robot is finding the correct color block and then brings it to Yumi. And then Yumi checks the color. Okay, now the pattern is already ready. So the idea is that these 2 robots cell can communicate with humans through computer. And then whatever I'm ordering there, these 2 robots can give it to me. Okay, at the moment it is a block pattern. But anyway, they're collaborative. I can be there close to them. And now it waits again for the next block pattern. Okay. Now I think that you can see this video. And now we'll take a closer look at how easy it is to program a collaborative robot. This is a quite long video, but it goes through the programming of the Omron TM12 robots shown in the previous picture and also in the previous video. It shows how it is programmed for a task where the robot searches for and picks up blocks from platform and pallets them into the desired 3x3 pattern on the platform. The blocks can be anywhere in the search area. And let's go through this program in flow format part by part. So first, a new project is created and named. So I have all the parts here so that you can see how easy it is to do. The robot program is made of this kind of a flow of program nodes. The robot moves are made with point node. Here is made a home point for the robot. Next, we have to make setups for the robot gripper in use. This step depends on the used gripper. For example, the gripping force, speed, etc. can be defined here. And now it's ready. The gripper setup gives OK or error feedback of setup according to its success. Now we use OK feedback, but of course in real situation we should define how to proceed in each feedback. Next, the robot is moved to the position as you saw here. And then the vision node is added by pressing vision button, and the vision node gives access to robot's camera and contains settings for image processing. A new vision project is added and named. And then Tommy goes back to the robot in this video part. The yellow cubes are placed to the camera's field of view. This helps setting up camera properties because of real situation image. In this demonstration, the automatic shutter time, gain, and focus setup is used. So all these are done here. It takes some time to do all that and then save. Now all these settings are made. Next step is to calibrate the camera image and the robot and the camera relation. This is done by placing a calibration plate to the camera's field of view and to the height of the object top surface. The camera searches specific markers on the calibration plate to make successful calibration. This is allowed from robot controller stick by pressing play button. Like that. Tommy did there. The robot needs to move above the calibration plate to make successful calibration. Sorry, it was already done, yeah. Here. The calibration takes some time. We have to make a couple of steps. But all these red marks here, they tell that we have succeeded in the calibration. Now, the robot moves to for calibration are automatically calculated by the robot. The robot just has to have enough space for moving. So we have to make sure that there's enough space for the robot to move above the calibration plate. Now it checks the plate from different fields of view so that it knows, that this is the calibration plate. And when I move, for example, 10 centimeters or 100 millimeters that way, how the field of view changes there. And then lastly, the workspace calibration is saved for the future. So we can use the same setup and the same calibration also in the future. Now the calibration plate and extra cubes can be removed from the camera's field of view. In this setup, just one cube is used for vision task teaching. Fixed point task is used because this gives possibility to tie up the vision coordinates to the robot's coordinate system. This means that later on, when robot points are taught on vision coordinate system, the points will move relative to the found cube. In this demonstration, the cube is searched from the image by using pattern matching tool, as you saw Tommy chose that there. First, in pattern matching tool, the pattern for searching is selected. So first is drawn there and then turned in the same angle as the cube is there. With all these, we teach to the camera that this is something that we are trying to find. After that, the found cube, the rectangle pattern there, is shown in the image. Next, the search area and search rotation are set up. The search area is here, the blue, and also the search rotation next. So as we have this rectangular cube, we give that the rotation angle can be something between -45 degrees to 45 degrees. Minimum score for acceptance and number of objects to find can also be set up. All the results and their values can be checked from the result table. Lastly, the vision tasks are saved and just made vision project is selected to use. Like that. Now, this is the node for the vision part. The moves and points for picking the yellow cubes are made next. The used coordinate system must be coordinate system from the vision node. Note that the eye symbol here in the node corner, all the next points for picking are made relative to the coordinate system. Points can also be added from the robot end arm button called point. The robot is easier to move to the pick point precisely from the robot controller window. This is the robot controller window where we can control all the axes and rotations. First, the z-axis was done precisely, and then x. And then OK. Now the robot is in correct place. Then another point node. This is the big point for the robot. The gripper's close node, so how to close the gripper, is added for closing the gripper fingers, and set run is used for closing the gripper and grip to the cube. There are different results for the gripper if there is something detected or not detected, or if there's any kind of errors. For the next robot points, the coordinate system is switched back to the robot base coordinate system. This is because next steps contain retract point and points for palletizing cubes in 3x3 matrix. These points can not be moving relative to the found cube. Now the robot is moved by hand. There is this button where the robot can be moved, and then, as you saw, Tommi, push the button when we got another point here. Pallet node is used to easily set up palletizing. The pallet node contains all needed properties like pallet pattern, rows and columns, area for palletizing, and number of layers. So with traditional industrial robots, we quite usually have to do the palletizing by ourselves. But here we have all the correct moves for palletizing. Large robot moves are made by hand and fine-tuning from robot controller. Now Tommi turns the robot controller on. For the selected pallet pattern, we need to teach 4 points. Starting point of the pattern, end point of the pattern, first row, and end point of the last pattern row. So the end, okay, now let's see how it is done. This is the second point. Now Tommi is moving the robot from the robot controller window. As you can see, the robot is now moving. Yeah, first point, second point, and third point. Now that was the second point, and it was recorded, and then the robot is again moved. Where's the end point of the last pattern row? And from those 3 points, the robot can itself calculate how to palletize these cubes. Now the number of layers and thickness of each layer is set here, and then OK, and then the pallet node is ready. After palletizing, the gripper fingers has to be opened for releasing and dropping the cube. So while here the gripper was closed, here it is opened. And now we have to have a situation where the gripper don't detect anything, then it's open. And lastly, the program is made to run in loop. Also, some arranging is made to clean up the flow editor. all this is just to clean up the flow editor so that it looks really nice. Like that, you can get all those in one column. And then the robot program is started from the controller stick. That little one there is this robot's controller. Notice that the gripper's rotation is minimal because the searching angles were defined from -45 to +45. And that's why the gripper is rotating minimally. On the left upper corner, we see the vision program results, how the object is detected, and then the coordinates are given to the robot. And then the next, now this cube was found, and then the palletizing is done according to the palletizing pattern that was defined earlier. Now Tommy is only here because he gives those cubes to the robot. The gripper is a bit sticky, and that's why these very lightweight cubes, when it opens the gripper, it somehow just drops there, and it's not in zero angle compared to the others. But for this example, this is very good. Let's check how the palette is ready. And then the last one. Okay. That was a long video, but I wanted to show you how simple it is to do. It is to program the robot. Okay, now it says that, okay, yes. I wanted to show you how simple it is to program the robot use this machine vision, integrated machine vision system, and also pick and place or palletize the cubes. And actually, as we know, there are lots of that simple tasks also in the industrial factories. Sorry. Okay. So we'll go. I have couple more examples here, but I just share you these links. This first one is from Opel's manufacturing, and the other one is an example how a robot and machine vision system works in collaboration. If you were a company manager or even a production manager, how would you feel if a product made it through your manufacturing and quality assurance processes with a defect and then landed in the hands of your customer? What if this happened over and over again? If hundreds or thousands of products over time end up with customers defective, what would it cost to your business? Time, product returns, stress, loss of customers, and possibility reduced profitability. At the end of this lecture, let's look a little at how robots could also be utilized in quality control. Quality control as part of manufacturing has often been carried out either as truly monotonous and tedious tasks where the worker only looks at the products on the line and tries to detect possible deviations, or as a part of the job description of all manufacturing workers. There is a general quality control obligation, or manufacturing is sampled at least once an hour, and the process adjustments and other quality improvements measures are made on the basis of it. First of all, does any of us people still want to do a job where we are just, watching the manufacturing, trying to recognize something? And are manufacturing workers certainly serious if they should monitor every product in addition to their own work? And thirdly, can we really be sure that low quality products will not be produced if quality control has been carried out, even on the basis of samples taken every hour? Quality assurance and inspection roles are ideal for robots. What is often viewed as a monotonous and highly stressful job for humans is easily filled by smart robots, and they won't complain at all. Robots with quality control capabilities are really welcome addition to nearly any smart factory. Not only can they repeat their job as many times as needed without even a minor deviation, but they can also inspect the smallest parts and pieces, perform microscopic measurements, and ensure uniformity on a level that the human eye cannot match. Okay, let's try one really quick activation task related to this lecture. I'd like you to write in the chat the 5 things you remembered about this lecture. Don't think too much, just write down 5 things that came to your mind about the topics of the day. I'm trying to identify from the chat and list here what are the most common topics that came to your mind. So please, I'll give you a couple of minutes, 3 minutes maybe, and you can write. You don't have to write any sentences, just a couple of words, but list 5 of the things that you remember from this lecture. I use this quite much with our university students because I want them all the time, try to figure out what they have really learned. And also, yeah.
Can I just have a question, because I
Yes.
just had it back at your kitchen robot already. It's just a curious question, maybe about programming. How did it recognize actually the next function it had to perform, either to pour another coffee or bake another wafer?
Yeah, then we didn't have those in that examples. example, but we planned it so that whenever the customer wants to have a waffle, then he or she pushes a button made for that. You know, when the button is pushed, then the robot knows that, okay, now there should be another waffle coming, and another button for the coffee order, you know. So just simple buttons. Push this button if you want to have a waffle, and push this button if you want to have a cup of coffee. Did you ask that?
Yeah, thank you. I just noticed that actually there was the cups were placed on this stand, and I somehow thought that maybe there was a link that it recognized that another cup is waiting. But yeah, this was the question actually. Thank you.
Yeah. Then just the customer pushes the button, you know, and also the customer could give the cup, but we also have this little machine that the students have done, which gives one cup at a time. Now I have to find you. Very good. There are really many answers already. Okay. Flexibility, simplicity, this end of the relationship. Flexibility and simplicity in programming. Very good. Maybe I have to, so that I can, now you can see that, but I can move this there so that I can see your answers, but also right here. Very good. Great attention to safety. Collaborative robots are cobots. Very good. Robot programming, easy. Cobot, collaborative robot. 250 millimeters per second, max movement without a collision specified. Sensitive skin robot, safety mat. Nice. Nice. I didn't say to you anything about that you should write down something while you were listening. So I'm really proud that you could answer so many things. So I have to write something down. Darko Mali, you have raised your hand. Would you like to ask something or comment? Can you hear us?
No.
Yeah.
No, it's a mistake thing. Sorry.
Okay. Yeah. Okay. Okay. Safety mode when collaborating. Safety, easy programming, small size. Very good. I have to write this down. I was present only half of the time, so I will write. Yeah. The mobile cobot. How easy can be programmed? You cannot use a toaster in your Great. It wasn't actually a toaster, and it was not big. We could use the waffle iron there, but we didn't have permission to use it in the frying mode because of some fire instructions or something. I don't know. It was quite. But we have another video where the all the ironing were done, or the waffle ironing was done in our machinery lab, where the fire instructions are not that strict. But now I have to write down something that you have. Yeah. Collaboration with humans. Max speed 250 millimeters per second in collaboration mode. Easy programming. Small size. else? Decision is always taken by humans. Yes. Now there's something. Okay, I did that. I mute because there was something coming to my ears. So decisions always done by humans. Very good. Yeah, difference between service and industrial robots. It wasn't the topic of today, but yeah, we went through that. Yeah, I'll put it here. Very good. And yes, that's also. And then yes, did I write everything? Sensitive skin. Yes. We will talk more about these sensors next time. So, and safety mat also. That's also very. I like it. It's somehow so, instructive or descriptive. I always see where I can be and where I can't be, and that's. I like it. Yeah. Okay. So now these are something that you have remembered from this lecture, and great. I'm really happy that you really remembered so many things. Again, okay. So these are some of the sources that I have used here when I was preparing this lecture. But of course, lots of the material comes from my lecturing material when I'm teaching the university students. And then lastly, you get another task where you can recall today's topics and reflect on their meanings. You can make a mind map of collaborative robots. I think that everyone knows what a mind map is, but here are some guidelines for that, for what this task is about. You can start by writing collaborative robots in the middle of your screen, your paper or picture, whatever you are doing. Then you can recall what has been going on today. And if you wish, you can also read more about the topic on the internet. I will share you all the links just after this webinar today. So you can go, for example, to the robotics blog, which I was talking about. Think about the key features, enabling technologies, benefits, and uses of collaborative robots, and write a separate title for each of them, combined with a line of collaborative robots. I hope you make a mind map with at least 3 levels of information. I'll show you an example after this. With at least 3 levels of information about collaborative robots. And please return the mind map as an attachment to me in email, and I will share them in chat because it was so complicated. I didn't notice that it was so complicated when you are coming out of from outside of our organization. It is so complicated to attach a file to the chat. So you can send the mind maps to me by email, and I will share them with your names on each of those, and I will share them to the chat. And again, deadline for this is the next training session on Friday. I can show you one example. This is an example of a mind map. not for this assignment, but in general, you know, there are 3 levels. This is the first level. This is the heating of the mind mapping software selection, and then there are ways to select or do when we are doing the selection, and then the third level, how the defining is done, how the ideating is done, how the prototyping is done, and so on. It can be like this, but you can use, for example, there are many free softwares that you can find in the internet, but reflect what you have heard today and also use all the knowledge you have before and make some kind of a mind map and send it to me. By the way, remember that you will get the certificate from this training if you have participated all these 3 webinars and you have done both of the assignments that I have given you here. So this is the second assignment. Do you have any questions concerning today's topics? Because now it's 5 o'clock in Finland and it's 4 o'clock there in the Central Europe. So our time is up. But if you have anything to ask, please don't hesitate to ask. I have time to answer. But thanks so much for being so active here. I liked how you wrote your thoughts to chat and how you participated also in the lecture. So I hope we will have the same kind of attitude also in Friday. Thanks, Frederico. Yes. Yes. Yeah. I can share you the presentation. Actually, I think that I already shared you the first presentation. Can you find it from the chat? I will share all the links and also these presentations. Okay, so I can try to share the presentation of the first time also again to you so that you can find it here in the chat. And then when you are returning your mind maps to me by email, then I will get your email addresses. And then after all these 3 lectures, I can also send you the slides attached in an email. If this is okay for you. But now that we leave this today, I continue working in the chat and I will share you everything from today's lecture.